In the last part, we looked into first order linear differential equations. In this part, we will look into second order linear differential equations. Now, these equations are again of two types, homogeneous and non-homogeneous equations. Let's begin with homogeneous equations. Therefore, we have the equation A, d squared y by dx squared plus b dy by dx plus cy is equal to 0. So, since we do not have any constant term, this is a homogeneous equation. And we are having a, b and c, these coefficients to be constants. So how do you solve this type of equation? For this, we are having a trial solution, which is y is equal to a e raised to mx. Now dy by dx will be equal to a m e raised to mx, and d squared y by dx squared will be equal to a m squared e raised to mx. When you put these values in this equation, we get a m squared e raised to mx plus b a m e raised to mx plus c a e raised to mx is equal to 0. This can be written as a m squared plus b m plus c into a e raised to mx is equal to 0. Now we are having two solutions here. One is the trivial solution, the other is a non-trivial solution. So for trivial solution, if we take a e raised to mx equals to 0, then we will definitely get y equals to 0. This is a trivial solution. To get non-trivial solutions, we'll take a m squared plus b m plus c equals to 0. So this will get m is equal to minus b plus minus root of b squared minus 4ac upon 2a. Now based on the value of m, we will have different solutions. So we get the value of m as m is equal to minus b plus minus root of b squared minus 4ac upon 2a. Now case 1 will be if b squared minus 4ac is greater than 0. If this value is greater than 0, we will have two solutions, two values of m will be m1 and m2. Both these values will be unequal, or we can say different, and they will be real values. Therefore, the solution y will be equal to c1 e raised to m1x plus c2 e raised to m2x. Case 2 will be if this b squared minus 4ac is equal to 0. Then the value of m will come out to be minus b by 2a. Thus the two values of m both will be equal to m1 and this will also be equal to m2. So both the values of m will be equal as well as real. Therefore the solution y will be c1 e raised to mx plus c2 x e raised to mx. Case 3, if b squared minus 4ac is less than 0. If that is the case, then the value of m1 and m2 will be unequal and they will not be real, but they will be complex quantities, like of the form alpha plus minus I beta. m1 will be alpha plus I beta, m2 will be alpha minus I beta. Then the solution y will be c1 e raised to alpha plus I beta x plus c2 e raised to alpha minus I beta x. Now you can also write this as y is equal to e raised to alpha I a cos beta x plus b sin beta x, where a is nothing but c1 plus c2 and b is I c1 minus c2. Now let's try to find the solution of this equation. D squared y by dx squared minus 2 dy by dx plus y is equal to 0. Now since there are no constant terms, this is a homogeneous equation, and this we are having here 2, that is the highest derivative is 2, so it is a second order. I can write this equation therefore as m squared minus 2m plus 1 equals to 0. Then the solutions of m will be equal to minus plus 2 plus minus root of b squared minus 4ac upon 2a. That will be 2 plus minus 0 upon 2, that is 2. Therefore, the two values of m will be 2 and 2. Right, so we are having 2 and 2 solutions of m. Therefore, our solution of this equation, that is y, will be equal to c1 e raised to 2x plus c2 x e raised to 2x. Now we are going to look into non-homogeneous second order linear differential equations with constant coefficients. So the equation will be of the type A, d squared y by dx squared plus b dy by dx plus cy is equal to sum r of x. Now this function or this term can be either a function of x or it can be a constant term. So here for these types of equations we are having two solutions. One is the complementary function, also known as the auxiliary equation, and the other solution is going to be the particular integral. Therefore the final solution y of this equation will be yc, that is complementary or auxiliary equation, plus yp, which will be the particular integral. Now how do you find each of these? To find complementary or auxiliary, complementary function or auxiliary, that is to find yc, what you will do is you will take this term to be 0. So for this we will only consider the equation A, d squared y by dx squared plus b dy by dx plus cy is equal to 0. This is a homogeneous equation, so just how we did for homogeneous equation, that is how you will solve this and get the value of yc. To solve this particular integral now, we'll consider d by dx as capital D, d squared by dx squared as d squared, and 1 by d as the integration with respect to this dx. So this equation I can write as a d squared plus b dy plus cy is equal to sum r of x. This can be written as a d squared plus bd plus c y is equal to r of x. This y is nothing but therefore r of x upon a d square plus bd plus c. This we call as f of d. Now depending on the type of this, what is this type of rx, we will get, there are different ways of getting y. Let's look into that. If this r of x is of the type e raised to alpha x, then y will be equal to e raised to alpha x upon f of d. Here we are going to replace d by alpha and therefore we will get y equals to e raised to alpha upon f of alpha. This is going to be our solution of this particular integral. Now if f of alpha comes out to be 0, then what do we do is we will take particular integral to be x e raised to alpha x upon f dash of d. You will differentiate the denominator and put an x here. Now we'll replace d by alpha and we'll get particular integral to be x e raised to alpha x upon f dash of alpha. So this will now be our solution of the particular integral. But if again f dash of alpha is equal to 0, if this denominator is equal to 0, we will do the differentiation again. So now we'll take the particular integral to be x squared e raised to alpha x upon f double dash of alpha. That means differentiating this again. So now we'll get the particular integral to be x squared e raised to alpha x upon f double dash of alpha. This will be our solution of the particular integral. Again, if this is 0, you will continue this process until you get a non-zero denominator. Let's try to find the solution of this equation. There will be two solutions. The first solution is going to be the complementary function, or you can also say the auxiliary equation. For that we will do m square minus 5m plus 4 equals to 0. We will take this term as 0. The values of m will be 5 plus minus root of 25 minus 16 divided by 2. That will be 5 plus minus 3 by 2. There are two solutions now. 5 plus 3 by 2, 8 by 2, that is 4, and 5 minus 3 by 2, that is 2 by 2, which is 1. Therefore, the solution complementary function yc will be equal to c1 e raised to 4x plus c2 e raised to x. Now we will find the particular integral. For that we will take our equation as d squared minus 5d plus 4y is equal to e raised to 4x. Therefore we will get y is equal to e raised to 4x upon, this is f of d square minus 5d plus 4. Now what I am going to do, I am going to replace d by alpha. Alpha here is 4. What do I get? I will get e raised to 4x upon 4 square, that is 16 minus 20 plus 4. You can see this denominator comes out to be 0. So we'll have to differentiate this. I'll take x e raised to 4x upon differentiating 2d minus 5. Again I'll put value of d as 4. I'll get x e raised to 4x upon 4 2s are 8 minus 5. That is x e raised to 4x upon 3, which is a non-zero denominator. Therefore the total final solution y will be complementary function plus particular integral. This is the particular integral y p. That will be, therefore final solution will be c1 e raised to 4x plus c2 e raised to x plus x e raised to 4x upon 3. Second case is that our r of x can be a polynomial function of x, that is of the term like this, a constant term plus some constant x plus some constant x squared and so on. So therefore we will get y particular will be equal to r of x divided by a naught plus a1x plus a2x squared and so on. For this there are steps. First step is to remove the lowest power term out from the denominator. Next step is to take this term, the denominator, into the numerator and make it of the form 1 plus x raised to minus 1 or 1 minus x raised to minus 1, or you can have 1 plus x raised to minus 2, or you can have 1 minus x raised to minus 2 and so on, and expand this. Now we will expand this and then take the differentiation. Now expansion will be only up to the order of the polynomial r of x. Let's look at an example. So to find the solution of this equation, we'll have two solutions, the complementary function and the particular integral, such that the final solution will be the complementary function plus the particular integral. So let's try to find the complementary function. We'll get m squared plus m minus 6, we'll take this as 0. We'll get the value of m as minus 1 plus minus root of b square is 1 minus plus 24 divided by 2. That is minus 1 plus minus 5 by 2. Again we'll have two solutions, minus 1 plus 5 by 2, that is 5 minus 1 is 4 by 2, 2. And we'll have minus 1 minus 5 by 2, that is minus 6 by 2, that is minus 3. Therefore yc will be equal to c1 e raised to 2x plus c2 e raised to minus 3x. Now we'll find the particular integral. For particular integral, we will take this as yp will be equal to 36x divided by d squared plus d minus 6. This can be written as 36x upon d plus 3 into d minus 2. I'll take the lowest power terms outside. I'll get 36x upon minus 2 out, and I'll get here 1 minus d by 2, and 3 out, and I'll get here 1 plus d by 3. Now this can 3 2s are 6, and therefore it will become minus 6x upon 1 minus d by 2 into 1 plus d by 3. Let's take these to the numerator and do the expansion. So I'll get here minus 1 minus d by 2 the whole raised to minus 1 into 1 plus d by 3 the whole raised to minus 1 into 6x. Let's keep this term as it is, 1 minus d by 2 the whole raised to minus 1, and expand this. Expansion of 1 minus x the whole raised to minus 1, as we have already seen, is nothing but 1 minus x plus x squared and so on. So this will be 1 minus x plus x squared and so on. But we have to do the expansion only up to the order of this polynomial. Order of the polynomial is 1. So we'll do the expansion only till 1, and we will get into 6x. We'll have minus 1 minus d by 2 the whole inverse. This can be written as 1 into 6x is 6x minus d is nothing but d by dx. So d by dx of 6x will be equal to 2. Now we will expand this. So we'll have minus 1 plus d by 2. Again we have to expand only to up to the order of the polynomial, because obviously the other terms will become 0. So this will be 1 plus d by 2 into 6x minus 2. This can be written as 1 into 6x minus 2 will be 6x minus 2. Now d is nothing but differentiation of 6x minus 2. Differentiation of 6d by 2 plus 1 by 2 into differentiation of 6x will be 6 and differentiation of constant will definitely be 0. So we'll get here minus 6x minus 2 plus 3, which will be minus 6x minus 1. This will be our particular integral. Therefore, the final solution y will be c1 e raised to 2x plus c2 e raised to minus 3x minus 6x minus 1. Third is when Rx is of the type cos alpha x or sin alpha x. Then we'll have yp will be equal to cos alpha x upon f of d, or it can also be sin alpha x upon f of d. So to solve these, we will replace d squared by minus alpha squared. Consider this equation: d squared y by dt squared plus y is equal to sin 2t. Again, this will have two solutions. The first solution is the complementary function. We'll have m squared plus 1 equals to 0. M squared is equal to minus 1. M is equal to plus minus I. Therefore, the solution yc will be equal to a cos t plus b sin t. The second solution is the particular integral, which is yp will be equal to sin 2t upon d squared plus 1. We have to replace d squared by minus alpha squared. So d squared will be, alpha here is 2, it will be minus 2 squared, that will be minus 4. So we'll have here sin 2t upon minus 4 plus 1, which is minus 1 by 3 sin 2t. Therefore, the final solution y will be complementary function plus particular integral, which will be a cos t plus b sin t minus 1 by 3 sin 2t. The fourth case is when r of x is of the type e raised to beta x f of x. Now this f of x can be either a polynomial of x, or it can be sin alpha x, or it can be cos alpha x. How do we find the particular integral in this case? That will be equal to e raised to beta x f of x 1 by f of d, right? Now what we will do is we will take this term out. We'll have e raised to beta x as it is, but then we will consider this to be d plus beta, and then we'll have f of x. Now we'll consider this term, and depending on the type of f of x, whether it is a polynomial or cos or sine, we will solve it as we have solved things in the previous cases. This is all for this video: second order linear differential equations with constant coefficients. In the next video, we will look into Cauchy-Euler equations, coupled systems of ordinary differential equations, and some other topics. Till then, peace be upon you.